Our next speaker is Luciana Basualdo Bonatto. She'll be telling us about an infinity opera of normalized cacti.
Thank you very much for the invitation and for organizing this really nice conference. I'm going to be talking about an infinity opera of normalized cacti, and this is joint work with Safia Ste, Abigail Linton, Sophie Rayner, Marcy Robertson, and Natalie Val, and it's a part of the Women in Topology workshop. So to start off, I'm going to tell you what do I mean by normalized cacti. So what are these things? Well, to start off, you should think of a cactus as this picture. And I'm going to unfold a little bit what it's all the data that is in there. So a cactus is a configuration of labeled circles. So what I mean by labels is that each circle, which I call lobe, comes with a number. So in this picture, I have a cactus with 8 lobes, and each of them comes numbered. And you can see this is a way in which the symmetric group can act just by permuting these labelings. Now, so this is this numbers in the numbers inside the lobes, and apart from that, we also have lengths. So we keep track of what is the size of the arc between the intersection points of each of the lobes. And you can see that the lobes can have different lengths. So this one is like 4/3, this is 1, this is a half. In principle, I put no condition on the length, but I need to keep track exactly what is the size of the arcs in the intersection points. Now, the condition of it being tree-like doesn't depend at all on an embedding somehow in the plane. This is a very graphical condition. So you can define a black and white graph associated to a cactus simply by replacing the lobes by white vertices and the intersection points by black vertices. And you say that a cactus is tree-like, a configuration of circles is tree-like if this dual black and white graph is a tree. And finally, the last piece of data in the cactus is a global base point, which is this point over here. Here it wasn't attached to lobe number 1, but it could be attached to anywhere. The space of all cacti with n lobes, I will denote cact n. Now, what does it mean for a cactus to be normalized? It means that the lengths of the lobes now I require to be 1. So I still need to have a global base point, and I have to keep track of all these ways, the lengths between the intersection points, but the total length of a lobe is 1. And I will denote the space of normalized cacti by cact1. Now, why would you start looking at the spaces? And well, first of all, they have a very nice CW decomposition, and it can be described in terms of these black and white graphs that I mentioned before. So I'm not going to go into too much detail on how it works, but you can define white edges to be sort of describing the arcs of the intersection points, the ones that you need to define to have a well-defined cactus. And then the K cells are induced by black and white trees with K white edges. So normalized cacti have a very simple CW decomposition, and non-normalized cacti are obtained, well, just by allowing the lobes to have different lengths. So it's homomorphic to normalized cacti with these extra parameters. So their topology is very easily described. Now, something nicer about this that was proved by Kaufman in 2006 is that they're homotopy equivalent to the 2 disks operad with n inputs, the space of the little disks with n inputs. So how can you visualize this? This is by no means a proof, but if you think of a cactus and you think of these edges as getting thicker and thicker as ribbons, you can get a sort of configuration of disks. And so since we can define a composition in the little disks, obviously, can we have something analogous to cacti? Because if we do, the fact that they have such a small CW model can be used for many, many things. So a first idea is to, well, let's try to work out this example. Here we have this cacti, which is now, if you think in analogy to the little disk, representing a two-array operation. So this disk over here is the input number 1, this is input number 2, and here I also have a two-array operation, and this bullet one means that I want to compose it in here. If you're trying to mimic little disks operation, what you can do is you can shrink the second cactus and put it inside the first. And I would just go back. So what's important is that this lobe has length 1. We will shrink this whole cactus to have length 1. And now, since the intersection was after a half, you have to follow what happens when you shrink at a half. And another important thing is that you align the base point of the cacti with the base point of the lobe that you're inserting with. If you, insert, for instance, at lobe number 2, you consider the base point to be this intersection point closest to the root. But in this case, you just shrink, put it there, and this is the composition that you have. So this looks really nice, and it makes sense with the little disks. Well, a problem if we want to talk about normalized cacti is that clearly the end result is not normalized. We started with 2 perfectly good normalized cacti, but we ended up with this, which has, well, these lobes have length a half each. So we want to define a composition for normalized cacti, and we could do the inverse process. So instead of shrinking, we could enlarge the lobe and then put the cactus inside. So now, instead of shrinking this thing to have length 1, we will grow this lobe until it has length 2, and then the intersection point will be at 1. So you just get this. So these are the 2 types of compositions. And now we can try to look at how they behave. So it's a result that cacti not normalized with this composition that messes up the size of the lobes. It defines a very good topological operad. Everything is associative, everything is well behaved. And actually it's a result that this is equivalent to the little disk operad. So here you go, one of the ideas of having like nice CW models to work with. Here you go, that's something we have. Now, you can expect that for normalized cacti, things won't be so simple, otherwise this talk would be really quick. And indeed, normalized cacti, this composition that we define is not associative. And if you're bored, this is a very basic example where this already fails. And you can try and work it out. If I would summarize in one word, why do this composition fail when it's so similar to the previous one? It's because now we're sort of not respecting the proportions of the lobes inside the cacti. So when we compose this thing, now the total length of this cactus is 3, and this lobe that before represented half of the proportion of the cactus is 1/3. But if you had composed something with more lobes, the proportion, it would be even less. So you're not scaling things in a nice way, like you're changing the proportions of things in the cactus. But you can move lobes around, you could walk with them, right? I mean, and you could guess like, okay, this composition is not associative, but I can show, if you give me 3 cacti, I can give you a homotopy that will connect these 2 ways of composing. So the next question is, can you do this coherently? So cact1 is not an operad, but is it an operad up to homotopy? Or in the language that we're using now, is cact1 with this composition an infinity operad? Well, a question that you should be asking now is, why are you still thinking about normalized cacti when you have a perfectly good operad of cacti to start with? And well, first, normalized cacti are still very useful, although the composition is not associative, because on a chain level, it is associative. So you have this very small model for the CW complex, and if you look at the operad that you get on the chains, has many applications, for instance, in string topology. So, so yes, people were still using normalized cacti. But we have another reason to think about this, which is more to do with the generalization of this procedure. So as cacti can be compared to the little discs, and this can be thought of as genus zero surfaces, oriented surfaces with boundary, you can also have graph models for surfaces which have more genus. So the moduli space of Riemann surfaces with at least one boundary component, oriented Riemann surfaces, has a graphical model in terms of fat graphs. So if you do that procedure of thickening these edges, you can see that you get exactly this torus with the boundary component. Now we want to define a composition of fat graphs that mimics cobordism composition somehow, and this was done by Daniela Santander in 2015. But this composition is not associative. And unlike the case for cacti, there is no obvious way that you can make it associative by changing the lengths of things. And now that you have multiple boundaries in which you can glue to do your cobordism, this thing that you can't rescale things all at once as you did for cacti. You really need to work out with these things that don't scale so well together, which is the case we have for Cact1. So by understanding normalized cacti, we have some idea of how to generalize things for fat graphs afterwards. And also we give an example of an infinity operad constructed from scratch, which, believe it or not, is not so common. So what are infinity operads? And actually more precisely, how am I thinking of infinity operads in this talk? Because there are many ways you can think about them. I guess the most well-known definition at the moment is this one due to Lurie. If you have never seen this definition before, don't worry, you don't need to understand all the details. It's quite involved. But as for operads, usually we can define a category of operations, and it both determines and is determined by its category of operations. This definition generalizes this. So it defines what it means to be an infinity category of operations and gives this as the data to be an infinity operad. I've never seen this definition being used to construct an infinity operad from scratch. And partly is because all this higher homotopy and the coherences that you have to build are implicit in like all this infinity categories construction. So all this coherence data is there, but it's more hidden. So if we want to construct it explicitly, we will use actually a model where these coherences are much more explicit. Another well-known definition is due to Szyszynski, Mordek, and Weiss, and it thinks of an infinity operad as a Siegel-dendroidal space. I really like this definition. It generalizes the way you go from a category to an infinity category via Siegel space, but now instead of encoding the Siegel condition using the category of simplices, here you use a category of trees. So this is really nice. Again, when we were trying to construct explicitly an infinity operad, this definition was still, a lot of coherences were hidden. So we actually ended up using a very classical approach to infinity operad, which is to think of it as an algebra over the WO operad. So here the WO, by WO I mean the W construction applied on the operad of operads. So this is very hands-on, and I will be talking a bit more about this third definition because it's the one that it's more explicit and it inspired us to construct this proof. But you should know that with the right adjectives, all these models are equivalent. So once we show that something is a WO algebra, we know how to, well, theoretically how to translate to the other definitions as well. So I mentioned an operad of operads. I will now just recall a bit, what do I mean by that? So you already know, or at least you expect, that it will be an operad whose algebras will be precisely operads. So to start with, we need to give for every natural number a space of operations. And this will be encoded by asking that this operand is n-colored. So the space associated to the color M, for instance, will encode the M array operations of our operand. And now the operations that have as inputs M1, MK. So I take an M1 array operation, an MK array operation, and I'm producing an N array operation. And this is represented by a composition. So you should think of this as trees of this sort. So in here, for instance, this is a tree where there's inputs, which I will call leaves, which are the edges that don't have end vertices on the top. Then it has 11 inputs. So this is representing something that is an 11 array operation, but it was constructing using a 5 array operation, a 3 array operation, and so on. The data that you have to give to specify this sort of composition then is a planar tree. You have to give precisely what are the vertices that you are using and how many inputs they have. And you also specify a labeling of the leaves. And this is going to give you the symmetric action. Okay, so now that an element of our operand is something of this form, how do we compose them? Well, here you have two of these operatic trees, and we want to use this tree representing a 4 array operation, and we want to compose with this one at 3. So here, 3 is representing this 4 array operation, and I'm going to replace it by this 4 array operation. So in the end result, I will get the tree, which is obtained by this one by taking off this vertex and replacing it by this tree. So yes, this is decoding precisely the idea that you got this 11 array operation by these compositions. And you have to be careful with the labelings. We described many labelings before. One of them is with respect to the vertices. So we need to be careful about this. So you have to follow the orders that is determined here, and also the label of the leaves. In this case, the label of the leaves agreed with the planar order of the leaves, so we didn't change anything. But in the next example, we can see how the symmetric action actually interferes. So in here, again, we want to replace this at 2. So 2 defined a 3 array operation in my graph, in my tree, and I want to think of it as this composition. And I marked this orange part because now the planar ordering of the leaves is not the same as the labels. So when I replace this, I will have to also permute what happens above this, this vertex. So what you get is, again, the vertex number 2 is replaced by this tree, and the leaves and the operation 4 is replaced, but now using this permutation described by the labeling of the leaves. Okay, now what we wanted, proposition, is algebras overall are precisely the one-colored symmetric operands. And I'm not going to prove this, but just a sketch, let's see that everything works. To give the data of O algebra P is, well, give first a list of, for any color, I have to give a space. So in particular, this has an underlying and graded object. If you look at the trees represented by this, so here I have only one vertex, which has n inputs. So this is just a corolla. And the only data you have on this corolla is the labeling of the leaves, which is acting by a symmetric sequence. So this is just encoding how the symmetric group acts on the space Pn. So this encodes a symmetric sequence, And if you look at maps of this type of trees, then they code precisely the compositions of your operations. And if you go through the details of exactly how do they compose, you see that they satisfy exactly the conditions you want for an operad. So this is very good. We have a operad of operads, and now we can use the W construction. So I won't have time to go into what the W construction of an operad is, but if you haven't seen it before, the slogan is that if you have an operad, the Borgman-Vought W construction, denoted WP, is an operad with the same colors as P, but now the WP algebras are up to homotopy P algebras. So if this is the slogan, you can right away think that, well, if O encodes is the operad of operads, then WO algebras will give me precisely operads up to homotopy. But the problem is that these things are really not nice. So this is the nicest drawing I can make of an element of WO. And the problem is, well, if you see the W construction, an element in there is a tree. So this is this big tree. And each vertex is colored by an element of your original operad. So in our case that we're using the operad of operads, each vertex is colored, is decorated by another tree. And you have all these labelings going around. And between every inner edge, you have a length. And it's very ugly. And it makes sense. The WO operad gives you operads up to homotopy, but it's very hard to work with this. And there is even one more word of caution, which is if you remember the W construction, the way you compose these big trees is by grafting, whilst the way you compose the trees in the operad of operads is by vertex substitution. So you have two types of trees. They don't even compose in the same way. It is a bit of a nightmare to actually show that something is a WO algebra just because it's really hard to use WO. So what we did is define another operad, which is what we call the operad of brackets. And that's what I'm gonna introduce now. So to start with, I'm gonna define what it means for a tree to be bracketed. And the image you should have in mind is this sort of thing. So you have a tree and you specify some subsets that are nicely behaved in the sense that you're trying to sort of give, well, parenthesizations or bracketings on how you should compose the elements on this tree. So this whole set of subsets is a bracketing, and each of them is called a bracket. Now, we ask for them to be nested and large. Well, by large, we mean that every one of the subset has to have at least two vertices. And the nested conditions means that if they intersect, then one must be contained in the other. Where does this come from? Well, an interpretation is just that we're trying to generalize the meaningful ways of putting parentheses on a word. So if you see, for instance, here, this is a perfectly fine parenthesization, but now this doesn't make any sense. And this translates to the condition of asking for the bracketing to be large because we want at least two vertices inside our parentheses. And this, the fact that this bracketing doesn't make any sense translates to the condition that we ask that the brackets are composed of nested subtrees. So you should think of this then as bracketings as putting parentheses on the vertices of a tree in a way that makes sense. And just as a remark, if you look at these examples, then these trees admit no non-empty bracketing. So first, because this one, you would be putting a bracketing around just one vertex, which is this case, which is not allowed. And in this case, the bracketing that you would put is not proper because it contains the whole tree. It's like putting a parenthesis around a word that has just 2 letters. It's meaningless. So, this examples of the corolla and the tree with just one internal edge are examples where you have no bracketing. Now, what we want this bracketing for is to actually encode not only the compositions, but also we want to keep track of all the possible ways you could realize this composition. And we want to actually specify the homotopies between all these different ways. So the way we do this is by giving each of these brackets a weight. So a weighted bracketing of a tree is, well, a bracketing where now each bracket comes with a number from 0 to 1. And this is called the weight of the bracket. Now you can think of it as, well, every tree that has a bracket now will have a cube of weights associated to it of the dimension of how many brackets you have there. So this is very similar to the W construction in the way that now from a tree, and in our case from a bracketed tree, we're associating a cube and we're going to glue them together. And the way you do this is by saying that if the weight of a bracket goes to 0, then you identify this with the bracketing where that specific bracket has disappeared. So this defines the space of, and we can call it the space of bracketings of T. And if you want an example, we can see, for instance, in this tree over here, we have a bracketing with 2 brackets. So the associated cube will be, well, just a square. You have one parameter that is determining the weight of the yellow bracket, and one parameter that is determining the weight of the red bracket. And you can see that if you bring both these weights to 0, then we're making it equivalent to making both these brackets disappear and having just the empty bracket. And you can always do this. So in particular, you can see that there will be a point here in the middle, which corresponds to the empty bracketing. And every cube will have a vertex there. Now, for instance, here you can see that this square is attached to this one where the yellow bracket has disappeared. So the yellow parameter has gone to 0, and then the green bracket is over here. So this is already quite different than the W construction. In the first, that you can expect that if you had this tree, then you would have a 3-dimensional cube because you have 3 internal edges. Whilst here we just have a 2-dimensional space because it's just corresponding to the possible ways of doing this composition. We have some more examples, and an interesting one is if you look, for instance, at trees of this type. So if you think of bracketings as possible ways to put parentheses on a word that is made by the vertices, then, well, the vertices here are just in a line. So to put the brackets is really just putting parentheses on a word. And that's why what you get is exactly the associahedra. More generally, this works for every tree where no vertex is connected to more than 2 inner edges. You can always arrange the vertices to be in a line, and then the bracketings correspond precisely to the ways of parenthesizing this word. Now, not all of the spaces are going to be associahedra. So for instance, if you look at this tree, you can still arrange the squares to form a polytope, and you can see that the vertices of the polytope correspond precisely to sort of maximal parenthesizations in the sense that, for instance, this bracket is contained both in here and in here, and it corresponds to a face. And it's sort of representing a homotopy between these 2 ways of composition. This is not a associahedra. And also, if you look at this example, for instance, which is for a tree now with 4 inner edges. This is also not an icosahedron, but these polytopes are actually well known and they have many names. So they're known as nestohedra, graph icosahedron, and also hypergraph polytopes. So now we're going to use them to define an operad of brackets. So we want to encode basically the same information of an operad together with homotopies between the different ways of composing. So, well, the operad of brackets is as the operad O, an n-colored operad. But now, instead of just having an operatic tree, we have an operatic tree with a bracket. So if you remember the picture you would have in mind for an operatic tree as a composition of the smaller operations together with a label of the leaves, then the tree that you get now for BO is this together with any type of bracket with a weight. So T here is a weight. Now, for this to be a operad, I need to actually define how you do the composition. And this is generalizing the composition of the operad of operads. So as before, here we want to replace this four-area operation with this four-area operation given by a composition, but also keeping track of and marking how compositions are made. So in particular, I want to keep this bracket. I want to keep this bracket that contains the four-area operation. And I also want to mark that this operation that will be included came from a composition. So that's why we get this bracketing in the end. So you can see that this first bracket just grows to include the tree that we included, and we also add this new bracket. I didn't add the weights here, but both of these remain with the same weight, and the new bracket that we add receives weight 1. So this is very much like the W construction in the sense as well that when you graph trees, you've created an inner edge, and this is an inner edge is assigned length 1. Now, the result that we have is that there is a canonical map of operads between WO and BO. And I won't go into detail on how this works, but basically you get that ugly tree that I had at the beginning with all the vertices decorated by other trees. And what you do is that you can compose all of them. So all of them are elements in the operad of operad. So if you do the composition that is described by this tree, you get this underlying tree over here in the operad of operads. Now for the bracketings, what we need to do is just see what are the subtrees that came from this composition. So this subtree over here is marked afterwards by the pink bracket, as well as the green one, and so on. And regarding the weights, you can simply take the weights that you got from the W construction and give it to the corresponding bracket. So this map is quite canonical and quite easy to define. And then, well, it's easy to see, to define is a bit messy, but a nice corollary that we get from this is that any BO algebra is in particular a WO algebra, and therefore an infinity operad. So we have this new operad that encodes a way of constructing infinity operads, and it's much, much easier to work with. A question could be, are they the same thing? BO algebras are the same thing as WO algebras. Can we use BO as another of our 1,000 definitions for infinity operads? And not really. BO algebras are a bit more strict. So if P is a BO algebra, then first of all, again, P has an underlying n-graded object. And if you look at the corollas, well, the corollas have no bracketing. So if you look at the space of bracketings of the corolla, oh, here should be B, sorry. The only thing that you're encoding is the labeling of the leaves. The only thing you're encoding is the permutations of the elements in P. The symmetric action in Pn. So far it's all the same as in the infinity operad, as in the operad of operads. Now here, if you look at what happens for trees of this sort, again, they don't admit any non-empty bracketing. So the space associated to this tree will just give you a map, which is a strict composition, but the associativity fails. So that's what encoded by the higher trees. But crucially, you have a well-defined composition, you have a well-defined sigma n action. And these are things that not necessarily every infinity operad will have on the nose. Sometimes you just have one up to homotopy. But in this case, so we're talking about infinity operads with strict symmetric action, strict composition, but that is not associative up to homotopy. So this encode all the higher homotopies. And this is exactly the case that we wanted to look at, because we want to look at normalized cacti with the composition we started with. So I guess now we can actually go back to normalized cacti, and the theorem that we have is that normalized cacti are a part of a BO algebra structure, and therefore they are an infinity operad. So I am not going to go into all the details of this proof, but I'm going to give you guys a sketch of how you can do this. So we have to start, well, BO is an n-colored operad. So to give the data of a BO algebra, first we need to specify, well, for each n, a topological space. So that's easy. That will be our normalized cacti. This part is done. But now comes the hard part, which is to give, for any space of bracketed trees, maps of this sort that are compatible with our operation of bracketed trees. So this is the hard part. Now, just to recall, so when we're talking about BO, we're talking about a disjoint union of spaces of this sort. So spaces of bracketings in a tree of operations. Now, if we start with a simpler tree, for instance, a corolla, then we discussed before that the corolla has no non-empty bracketings. So the space of bracketings of the corolla is just the elements of O that are associated to this corolla, which just have to do with the labelings of the leaves. So this map will just record the permutation of the labels of the lobes of the cactus that we described before, that's the symmetric group action in there. Now, if we look at another simple tree, so this tree over here, as before, we mentioned that this tree has no non-empty bracketing, because any bracketing here will just be a parenthesization of two letters that is not helpful information. So the space of bracketings of this, again, is just discrete. You don't have this homotopies filling in a polytope. So when you give a map of this sort, you just want to actually give a composition, and we have a map for this. We have our chosen composition from the start. So these maps are also chosen. Now, what we need is to define these maps for the polytopes associated to more difficult types of tree. An important thing to realize is that once you have defined what it does on these types of trees, you have actually defined this map on the vertices of your polytopes, because as I mentioned before, the vertices of your polytopes correspond precisely to the maximal bracketings. So the bracketings that define a complete composition. So this, in a way, we already know where we want to take the vertices of our polytopes, but we still need to find a way to construct these paths between them in a coherent way. And this is what we need to do. Now, the key step in this proof is that we go out of cacti a little bit. So for each tree, we have a convex space, well, MT, and a map that I will call the reparameterization map. So if T has a vertex with C1 input, a vertex with C1 inputs, and then a vertex with CK inputs, then my renormalization map takes this and sends to one cacti with where C is the number of inputs of T. So it is sort of doing a composition of this cacti, but together with some sort of renormalization parameter. And a key aspect in here is that if I give a cactus that is given by a composition of x1, xk, according to a bracket of T, I can choose a canonical element in this MT recording reparameterizations, such that I reparameterize and I get X. So I think the crucial step is that we found renormalization maps that have as a parameter a convex space, and you can find ways to express the composition of cacti using these reparameterizations. Now, if you have a canonical M for every such bracket, in particular, you can map the vertices of our polytope to this M. So if I have a given bracket on a T with, let's say, all the weights equal to 1, then if I map this bracket, a specific bracket of the T to M, I get a map of this sort. And even further, since M is a convex space, then we just get a map from BT to the entire of MT. So why does this help us? Well, because then to construct our maps from BT to CACT1, we can go through this middle step, which is this convex space MT that we defined. Now I know that this convex space MT with this reparameterization action seems as if it came out of nowhere, but the good thing is that it actually has a very nice and geometrical interpretation. So I'm gonna give the last bit of this proof, which is what is exactly is this convex space MT and how does it act by this reparameterizations. So the key idea is that a cacti can also be thought of as or described by a partition of its outer circle. So over here, for instance, we have a circle that would be of length 3, and we can rescale it. And then, well, the part of the circle that will go around lobe number 1 will have length 1/3. And if I put the base point over here, it will be precisely corresponding to this thing. So we have a way to, given a cactus, obtain a partition of the circle. This was defined by Salvatore, and not all these partitions are going to correspond to cacti. So in particular, we need, we couldn't have the colors interchanging so much. So if it was green and pink and then green again, if you put them together like this, it wouldn't be a cactus, it would have loops. So not all partitions of the circle are correspond to normalized cacti, but crucially, all normalized cacti define one of these partitions, and it is unique. So in this way, we have a way of mapping the space of cacti to the space of partitions of the circle, and now we can act on the space by monotone maps of the interval. So if I have a map, well, I'm thinking of maps of the circle as monotone maps of the interval that fix the boundary. So this gives me a map of the circle that fixes the base point. And you can see this as a way of reparametrizing the partitions of the circle. And again, not if you act by a random strictly monotone map, you might not get something that is the outer circle of a normalized cactus, in particular because in this case, all these partitions have equal length. So since all the lobes in the cactus had length 1, if you add up the lengths of these colors, you also get that they have to have all the same length. And if you reparametrize it, this might not be the case. But you can always renormalize it in a very nice way to get back to normalized cacti. And that is the strategy we use. So the convex space that we use, that I mentioned before, will actually be a product of the space of strictly monotone maps from the interval fixing the boundary. And the key step then to finish the proof is just to find ways of representing all the cacti compositions with all the meaningful brackets as just these actions of these reparametrization maps on this product of cacti. So once you do this, then basically you can just linearly interpolate in this very nice polytope that we created, and you've got a map from the whole of BO to your cacti. So this finishes the proof that cacti are an infinity operad. And well, what we're going to do next is to look at how you can use the exact same strategy to understand fat graphs. So I'm not going to talk about this today, don't worry. But so we constructed this operad of bracketed trees. We have now an operad that encodes all the homotopies that we need to construct an infinity operad. And now we are just going to use them to this next step to construct an infinity operad of fat graphs. And I guess that's what I wanted to say. Thank you very much.
Thank you, Lucy.